so it was uh, so it was known that the photons, sorry, it was known, that light is a wave, but then an experiment in the early 1900s sort of showed that light was behaving like a particle. And I guess I got to be a little clear with the nomenclature here. I'm using the word particle to describe all these elementary entities we're talking about. And usually, when you hear the word particle, you sort of think of something like a billiard ball that maybe is at a little point, tiny little point, and bouncing around off each other. And a wave is something else. But what? But these so light is sort of behaving sometimes like a wave and sometimes like a particle. Uh, and then electrons in the 1920s was an experiment that showed that electrons would behave like a wave. They would diffract just like a wave would. And so there was uh, this duality of these elementary particles, and I'll use the word particle for them still, but this dual nature, and that was sort of first put together in a mathematical physics theory called quantum mechanics that came about in the 1920s. And I just love this picture here where all the great physicists of the time were all gathered together. We have here in the middle Einstein, uh, and Madame Curie, who was involved, who discovered radioactivity. We're going to talk a little more about that. Max Planck, who would that particle nature of light. And in the back here, we have a lot of the people who've put together the quantum mechanics in the 20s. We got Schrodinger. He had the Schrodinger equation. There was Heisenberg. He had a different equation, which turned out to be mathematically identical. It looked different, but it was like the same. And he came up with an uncertainty principle that we'll talk about a little later. And we have Pauli, who Antonio mentioned was one of the first people who talked about neutrinos. Uh, he had something else called an exclusion principle. Here's Dirac. He extended quantum mechanics to a quantum field theory. We'll talk a little about that. And he was the one who predicted antiparticles, which is what was seen. And over here is Niels Bohr, who had several important uh, accomplishments here in contributing to quantum mechanics. But one of his biggest accomplishments was trying to explain it because it's very hard to understand. We understand life at the macro level, the world at a macro level, but trying to understand what these particles are doing, that when you measure them, well, you can't actually measure where they are. And until you measure them, well, what they could be in two different states. And are they, until you measure them, they don't go into those states, all these things that don't make a lot of sense. So he tried to explain it, which, and still, to this day, very hard to understand what quantum mechanics means. But anyway, let me get back to the story here. We're moving now into 1930s. So radioactivity actually was discovered earlier. That we have atoms that spontaneously decay, and they decay identified in three different ways. But let me focus on the one called a beta decay. So in a beta decay, you have an electron that sort of pops out of a nucleus, and the nucleus changes uh, by plus or minus one in terms of its atomic number to a neighboring kind of element. So because I'll have one or one more or one less proton. Assume beta particle, I said, is electron, but it could also be a positron. So you have before and after state of the nucleus, you give off an electron. Those states should have a fixed energy difference. The beta particle should have a fixed energy, but instead it had a spectrum of energy. So how could that be? How could we conserve energy? So that's what led Pauli in the early 30s to propose that there's a very light, chargeless particle that's also created in that beta decay, and it's taking away the energy momentum that you don't see in the beta particle. So uh, that was actually a pretty radical idea. And Pauli himself was a little concerned that he invented a particle that he figured you'd never be able to see. Uh, However, as we'll see, we actually have seen them. So then actually, I think he called it the neutron, but at around the same time, the neutron was discovered. So and the neutron held for the particle that's in a nucleus, the heavy particle in a nucleus. So it was Fermi that the Italian physicist who added so meaning a little neutron. So now we have neutrinos, and Fermi then created this theory of beta decay, with neutrinos in it, and was able to predict how rates and so and the particles that would come out in reactions like that. And then it could be extended to other things beyond just beta decay, that fusion, fission, those processes were all involved with neutrinos. And so, this whole set of uh, processes and theories, what became called the weak interaction, because anything with a neutrino you can very hard to see, and it doesn't happen very frequently. So compared to electromagnetic things where or the forces that still don't understand at this point that are holding together the nucleus. That theory was extended in the 1950s by Li and Yang to a more general theory. Other pieces of the puzzle have come together as there were more and more experiments. And one of the key experiments in the 50s was done by Fred Reines, who actually was able to see interactions of neutrinos in a detector that was right next to a fission reactor. And so, that was the first experimental evidence that there really was a neutrino. All right, so let's just move on. We physicists now, learning more about all these elementary particles. The first accelerator was cosmic rays. So the Earth is being hit from all directions by these high energy protons, that are the cosmic rays, which are basically high energy protons. They hit the atmosphere, they create other particles, and physicists went up on mountaintops to see these cosmic ray interactions with detectors up there, and they were able to see for the first time. They were able to see that there really were antiparticles. That was the positron was discovered, and then there were particles that seem to be associated with nuclei called pions that would pop in and out with short-lived particles, and then other particles that seem to be acting like a heavy electron called muons. So we're starting to see different particles. Uh, Next big event was extending the quantum field theory that Dirac had started to fully explain electromagnetism in terms of this quantum field theory, and led to Nobel Prizes to Richard Feynman and others. And he created this diagram which tried to explain it, both explained at some level what was happening, uh, and also was a method to be able to calculate almost anything. So these Feynman diagrams were a very powerful thing that the particle physicists, been using since the 1940s to understand the different interactions. Well, so, but move ahead to the 50s, we start building accelerators because it's hard to, go up to mountaintops and try to see the cosmic rays, and we see a lot more particles, a whole particle zoo, a lot of, dozens of heavy proton-like particles. We call them baryons, dozens of heavy pion-like particles. We call them mesons. And we have the electron and the heavy electron. The muon, turns out there's a heavier electron that was eventually discovered called the tau particle, and then each of them had an associated neutrino. So we got all these particles. So how did we make sense of it? And that's what happened in the now in 1960s and 70s. The idea that all these particles are made of quarks, not all these particles, the baryons and mesons are made of quarks. So they're not fun, they're not the protons and neutrons are not elementary particles. They have components called quarks, and these quarks have fractional charge, one third, two-thirds charge. Um, very interesting idea. No one has actually been able to detect a naked quark and see a one-third charged particle. Whenever you hit, have a high energy collision and you might be making quarks. They quickly surround themselves with other quarks and never have just a single uh, quark that you can see experimentally. But the physicists are convinced that they're there. So it's led to the theory of strong interactions, which is sort of the question, why is the nucleus held together? And so the quarks are interacting with each other via gluons. So a new particle was proposed that would be interchanged between quarks to hold them together, and all experimental evidence shows that this really was correct. And at the same time, we had the weak interaction, electromagnetic interaction. They seem very different, but uh, let me not get into any details, but the they were shown, to be sort of the same uh, manifestations of the same force that just sort of at low energies sort of looks very different, but at higher energies sort of becomes the same. And so all of this together became what's known as the Standard Model. And this next slide shows all the particles that are in the Standard Model. I'm not going to go into a lot of detail here, but we have this first column, the first generation of particles, which have the particles we know of, the stable particles, the electron and the quarks, the up quark and the down quark that make up the proton and the neutron, and the electron neutrino. But like I said, there's a heavier set of particles that basically behave the same way, except because they're heavier and the weak interaction allows them to decay to lower mass particles. These don't have very long lifetimes. You measure them in the milliseconds or microseconds or nanoseconds or less. Right? And a third generation was discovered. And each generation has its own, has the muon and the tau here, and the muon neutrino and the tau neutrino. You have the particles that are uh, mediating the force. And then you got this other particle, which is the very last particle actually seen in this page, experimentally shown. The Higgs particle was predicted in the 60s, and it was needed to give mass to all these particles up here above this squiggly line. So finally, when it was discovered, it sort of completed the Standard Model. But there are many questions in the Standard Model. Let me, like why are there three generations, among other things. But one of the things that's interesting here is that the neutrino should be massless. So the Higgs mechanism does not give mass to neutrinos. But below this squiggly line, you see numbers here. This is a 6 order of magnitude. The reason is the squiggly line is a 6 orders of magnitude drop. So the mass of these particles, and we don't really know the mass yet. That's one of the important things we have to do is measure these masses. But they're more than 1 million times less than the electron, which is the lightest of all these particles here. So it's non-zero but tiny. No one know, we don't know why yet. Hopefully, that'll be something that we'll learn soon. Uh, Now, so this is the time that I started grad school. This Standard Model was complete, and the theorists at the time, didn't want to stop there. They said, "Gee, we were so successful in unifying the electromagnetic force and the weak force. What can we do something similar with a strong force?" So this axis is showing the strength of the force. This axis is showing the energy. So you had to go to these energies, which are achievable in accelerators, to sort of show that these, get phenomena associated with the electromagnetism and weak force put together into electroweak force. Well, you can sort of extrapolate the strength of these electroweak force and the strong force, and they would come together someplace out here 13 orders of magnitude higher in energy. And if it did, there could be new phenomena that would happen. There would be new bosons that would mediate new forces. And the force that this boson would mediate would be a force that would allow a quark to turn into a lepton or vice versa. Because I forgot to mention, but in that standard model, you got quarks, they can decay into other quarks, but you can't have a quark turn into a lepton or vice versa in the standard model. But with this unification and with this X boson, you could do that. And what would happen if you could do that? Well, the quarks that make up a proton could turn into a positron and an antiquark, and that would mean that a proton would turn into a positron in a short-lived meson that would decay, and you could see all of this in an experiment. Well, in principle, you could see it in an experiment if you could build an accelerator 13 orders of magnitude, more than anything we have today, which of course is, impossible. But there's another way to go, because this Heisenberg uncertainty principle, you could express it as your error in measuring energy times the time is less than this very small number. What it means is that we can violate conservation of energy for a very short time. And so this X boson at this enormous mass could suddenly just pop out of the vacuum, do this interaction up here, and cause the proton to decay. And you could calculate the probability of that. And the probability is that would happen with a lifetime for the proton of 10 to the 31st years. Really big number, because the lifetime of the universe is 10 to the 10th years. So, 21 orders of magnitude longer than the age of the universe. But we got something on our side, Avogadro's number, right? You can get a lot of protons in a small space. And even 10 to the 31st protons, that's only 100 tons of matter. So if got together 100 tons, and this was really true, we'd see one decay a year. So this is sort of possible. And so I start graduate school, and I meet my professor, became my thesis advisor, Larry Sulak, and he comes back from a conference where the theorists had said this is the greatest experiment that could be done. And so the two of us come up with a blueprint. In a few months, we come up with a blueprint on how to do this experiment. And then over the succeeding months, we worked together with a group from Irvine and Michigan and Brookhaven to create what was called the IMB experiment. And and the experiment that was built was very close to this blueprint that we put together. The experiment, so how are you going to look for this? So first of all, 100 tons doesn't cut it, because you're not going to look for one decay a year. So we want 10,000 tons, so we're getting at least 100 decays a year. We're not waiting very long to see the proton decaying. We got to go underground, because we'll be overwhelmed by cosmic rays hitting us on the surface. So we put this 2,000 feet underground in a salt mine outside of Cleveland. And what's the best way to get 10,000 tons, or let's say the cheapest way to get 10,000 tons? Well, water is a pretty cheap medium. So we build a tank and fill it with water, and we purify that water. And so here, this picture is taken in that tank with a diver that's actually in the water. So you can see across, it's like 70 feet across in this detector. It's pretty much cubic detector. We have these little circles that show up here are photomultiplier tubes. I'll get to that in a moment. And there's 2,000 of them on all six. A total is 2,000 across all six sides of this cube. So anything that happens in the middle that gives off light, and I'll talk in a moment how we give off light, can be detected by these detectors. And these detectors, these photomultiplier tubes, can actually detect single photons of light. So this experiment, the problem is that there's a background coming from neutrinos that are being generated in cosmic ray interaction, because we're looking for a proton somewhere in the middle to suddenly spontaneously decay. But a neutrino is going to sneak into the tank, and of course going to sneak out, because they hardly ever interact. But approximately one a day from these neutrinos from the cosmic ray are actually going to interact somewhere in the middle of the detector. So we got to be able to distinguish those interactions from the cosmic ray. So I mean, from a proton decay. And how do we do all of this? So it's so the trick is something called Cherenkov light. So it was predicted in the 1930s and experimentally shown, but this was the first time it was really built in a large scale detector and used to reconstruct particles this way. And so the idea is, let's say we have a particle that starts over here. By the way, I presume everyone's able to see my cursor move.
Yeah.
Oh, yeah, good. Okay, so so the particle starts here. Let's say it's heading straight for this wall of the detector. Well, a particle here will typically be pretty relativistic. From a proton decay, if those E plus and pi zeros, they'll have enough energy that they'll be going close to the speed of light. Now, speed of light is the universal speed limit. Sorry, I should say different. The speed of light in vacuum is universal speed limit. Speed of light in water is only like two-thirds the speed of light in a vacuum. But these particles have enough energy to go, almost the speed of light in a vacuum. And they can go therefore faster than the speed of light in water while they're in water. And what happens, this Cherenkov effect, is that very similar to when an airplane goes faster than the speed of sound, gives off a shock wave of sound. So this particle going faster than the speed of light in water gives off a shock wave of light. And the light comes out at a specific angle to the direction of the particle. So while the particle is relativistic here, but it's losing energy slowly as it goes through the water, and eventually its speed drops below the speed of light in water, and then it stops giving off Cherenkov light. But while it's giving off light, that light sort of comes off in a cone, a cone around the particle, and then when it intersects this edge, the detector, there's a ring of these photomultiplier tubes that see the light, and the other tubes don't really see the light. And so, by virtue of the topology of these rings, the time between when the light is seen from one side to the other, and so on, we're able to reconstruct back to where the particle started, how much energy the particle had, and the direction it was going. And so this could be a neutrino interaction coming in and making a single particle. But if we had a proton decay, the proton's sitting here at rest. So the proton would typically give off two particles. The proton decay would give off two particles. And because there was no momentum to start with, these particles would come off back to back, 180 degrees apart. So you'd get a ring on one side of the detector, a ring on the other side of the detector. This is just a two-dimensional slice here, but you'd see two different rings, and you'd be able to reconstruct that they came from the same point here. And if this angle was close to 180 degrees, well, it's really indicative that you saw a proton decay, because if a neutrino is coming and interacting, it's coming in with a lot of momentum. So whatever it makes in the detector is going to tend to go in the direction, that the neutrino is coming in. And, very rarely would you see two particles coming anywhere close to back. So, this way we're able to suppress that neutrino background. So the experiment, the IMB experiment, started running in 1982, and by 1983 we had enough data to publish paper, and people expecting a Nobel Prize from seeing a proton decay. Well, oops, wrong. So guess what? We saw nothing, right? In that first year, we saw nothing. And we're able to set a limit that the proton lifetime had to be greater than the first paper, 6.5 times 10 to the 31st year. So it's also already getting into where the theorists said we should have been able to see things. Well, guess what? Let me just move ahead another 40 years. No one's seen proton decay. There have been many experiments looking for this. Their lifetime limits now, they're up to 10 to the 34th years. So this idea of grand unification, or at least as it was initially proposed, is not right. Maybe there is a unification that does occur, but it doesn't occur as simply as the theorists in 1978 thought it would. Anyway, so I got my thesis at the same time. I looked, and my thesis was about a different decay mode. Also, of course, didn't see anything. But what we did notice, because with my decay mode, I had to understand the neutrino background a little better. We saw that there was a deficit of muon neutrinos. So, muon neutrinos coming from the cosmic ray interactions. That deficit, was a little significant, but not significant enough to be any discovery. But it sort of led to the question of why. Why would there be a deficit in neutrinos? And it moves us to the next step here, where uh, possible reasons for that is something that's called neutrino oscillation. So it's back to those non-massless neutrinos, right? So they should be massless, and no one has directly measured mass of a neutrino. But suppose they had a non-zero mass, and they're created at some point and they propagate. Oh, by the way, not only have a non-zero mass, but the different neutrinos have different masses. They have to have different masses. So you get this quantum mechanical interference with each other because the particles are now they have a mass. They're not going quite the speed of light. They have tiny mass. Not an unmeasurable difference between the speed of light and the speed of a neutrino. But they this quantum mechanical mixing interference that occurs potentially allows the type of neutrino to change as it propagates. And that would be a function of energy. So the higher energy, the less of this would happen. The more distance, the more the mixing could occur. And the bigger the mass difference between the different types, more the mixing could occur. Of course, there has to be a coupling constant that's non-zero that would even allow it to occur. So there's something like six parameters that because there's three neutrinos that would you need to understand to fully explain the neutrino oscillation. Well, and so how does this show up? Well, so here we have the experiment, right? And we have cosmic rays coming, hitting the atmosphere a few miles above the experiment and coming down and into the detector and being detected. But we also have other neutrinos that are being made the other side of the Earth, and they've gone 8,000 miles before they come in the detector. So these neutrinos from the other side have a much higher chance of oscillating. And now there's both muon and electron neutrinos created in these cosmic rays, but there's many more muon neutrinos than electron neutrinos. So the net effect of the oscillation would be to reduce the number of muon neutrinos that you see. And so that could explain what we were seeing at this point. But there's other ways to look for neutrino oscillations. Let's go to the sun. So what's happening in the sun? Fusion's happening in the sun, giving off neutrinos, and those are electron neutrinos, only electron neutrinos that at the energies that fusion occurs. Well, that electron neutrino has a probability then of changing into a muon or tau neutrino when it reaches the Earth, which, by the way, would then be almost invisible because there's not enough energy to make a muon or make a neutrino, or make a tau neutrino, muon or a tau particle from a muon neutrino, a tau neutrino. But you do have enough energy from an electron neutrino to make an electron. Let's just talk about fusion just a little more, right? So what's happening in the sun, right? So, sun is burning, fusing hydrogen into helium, and that's the main reaction that's occurring in the sun, and it's giving off these neutrinos here that have the highest flux. We also have the lowest energy. And these neutrinos at this low energy, well, they don't even have enough energy, to make an electron, let alone a relativistic electron. So those neutrinos are not going to be very useful in a water detector. But there are other fusion reactions that are occurring in the sun that create boron 8. And that decays and gives off neutrinos that actually go up to like above 15 MeV. There's other neutrinos that go slightly higher, but they're down by like three orders of magnitude. So you're not really able to see, almost everything you're going to see is coming from the boron 8 neutrinos. So you want to understand the boron 8 neutrinos with what? Well, now can we actually see this with these numbers, right? So these are energies. I realize most of you are not, familiar with the scale of energy, but the mass of the electron is over here at a half an MeV. So some place up here, the electron gets very relativistic, and we somewhere above 2 MeV, you can see the Cherenkov light in principle, but of course it's very hard in a detector to see tiny little amounts of Cherenkov light. The experiment that I worked on, the IMB experiment, at the time I worked on it, could not see anything, below 20 MeV. No way. Uh, Now, there was an experiment that Ray Davis had been running since the 1960s in a mine in South Dakota, Homestake mine in South Dakota, looking for neutrinos from the sun in a tank of cleaning fluid, with mainly chlorine. And the neutrinos, these neutrinos, would hit, neutrinos above this energy threshold here would mostly, again, boron 8 neutrinos would hit the detector and convert chlorine to argon, a radioactive argon that had something like a 1 month lifetime. And he was able to chemically separate the argon, individual argon atoms almost out of this detector, and then count how many decayed. And 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 the number that he came up with was significantly less than what was predicted from these boron 8 neutrinos. Of course, you didn't even know if he was detecting neutrinos from the sun. There's no way to know it was, solar versus a terrestrial neutrino that might have been coming in and doing this. But this was another potential indication, that there is neutrino oscillations. But anyway, there's another experiment that had been built around the same time as the IMB experiment, called the Kamioka experiment, and that experiment had more light collection capability than the IMB experiment. IMB experiment, so we sort of ran out of budget to put in more photomultiplier tubes, right? But Kamioka was able to use bigger tubes, and it was a smaller detector, so they were able to afford it, and came up with a threshold which, we calculated the threshold we should be able to see something was around 8 MeV. So you'd be able to get a, reasonable fraction of these boron 8 neutrinos. Uh, this is a log scale, so it's a little misleading on how many there are. But so you get a reasonable fraction of the boron 8 neutrinos. So I decided to leave the IMB experiment and go work on the Kamioka experiment to try to see neutrinos from the sun. Because not only could we maybe learn about neutrino oscillations, but we can also tell it came from the sun, because the neutrino will interact, create an electron, and that electron direction will point back to the sun. So I joined the experiment along with the University of Penn. What we needed to do was upgrade the electronics. The existing electronics was not going to work to be able to see at these low energies, but so we did upgrade the electronics. We started running in early 1986 with the new electronics, and we eventually, this experiment in 1989 was a published paper that said, we've seen solar neutrinos because we can see that they point back to the sun, and it's coming in around, less than half of what was expected. So this was definitely an indication of neutrino oscillations. Wasn't a discovery yet of neutrino oscillations, because those boron 8 neutrinos had a lot of uncertainty in the number, the flux that was expected. We know how much energy the sun's giving off, but it's almost entirely in those hydrogen to helium neutrinos, and the boron 8 neutrinos, were just a fraction, less than 1% of the energy of the sun is involved in that, and so, there was some, very sensitive to things like the temperature of the sun. So a lot of, potential systematic errors. So it wasn't yet a discovery, but look, 1989, neutrinos from the sun. God, we've invented neutrino astronomy. We've seen extraterrestrial neutrinos. 1989. Well, so did we discover in 1989? Well, the answer is no, because something happened before that. So while we're trying to get all the data to do this, There happened to be a supernova. The last supernova that occurred was around 400 years ago. The last nearby supernova occurred like 400 years ago. And what happens in a supernova? So you have a star, like the sun is burning. I'm using the word burning to mean fusion, hydrogen into helium. Well, it then eventually you run out of hydrogen, but then the helium starts to burn into carbon or something heavier, and then you run out of that, and then it burns into something heavier, and you run out of that. Meanwhile, while fusion is going on, the stars is stable because it wants to collapse on itself from gravity, but it's got this radiative pressure from the fusion that's keeping it stable, that's pushing out and keeping it stable. So this continues. We go to higher uh, uh, elements. We go to silicon, and silicon burns into iron. And so when we run out of silicon, we just have iron there. And when you have iron, there's no more fusion that can occur. And so suddenly, all you have is the gravity trying to collapse the star, and the star will collapse probably into a neutron star. And if the star is massive enough, it'll even collapse into a black hole. But as it's collapsing, it sort of rebounds and explodes. Most of it collapses, but some of it explodes, and that explosion gives off light that we've seen optically. Well, not from nearby neutrinos, but from telescopes. We've seen it all over the place. In galaxies up, billions of light years away, uh, and it gives off most of the energy actually in neutrinos. And what happened in 1987? Well, February 1987, light from a supernova in the Large Magellanic Cloud, which is 170,000 light years away. So this light was traveling 170,000 years, and it hits us, hits the Earth, hits our detectors, hits the telescopes. So people see this supernova, the first nearby supernova in 400 years. But both of the experiments I worked on, the Kamioka experiment, the IMB experiment, both saw neutrinos from the supernova. So the IMB experiment had been upgraded, so it was able to detect to lower energies and make things better. Neutrinos, the supernova neutrinos have a little higher energy than the boron 8 neutrinos. So that they were detectable in the IMB experiment, they were detectable in the Kamioka experiment, and there was another experiment in Russia that was able to see some. So, and here's a chart sort of showing the time frame that these neutrinos came out in, over like a 10-second period. Of course, these experiments were not exactly synchronized. This was pre-GPS. Uh, I think all the experiments, the timing was basically based on someone with a watch typing, a clock on a computer at the time. So, these were only sort of synchronized maybe to seconds, but, it basically, it all came out at the same time. And, we saw neutrinos from a supernova. This was the beginning of neutrino astronomy. And 15 years later, the Nobel Prize was awarded to Koshiba, the head of the Kamioka experiment, and Ray Davis of the Homestake experiment for their pioneering detection of cosmic neutrinos. Well, let's go just 20 years later, it took a little longer, but the American Physics Society decided not to give an award, but they unveiled a plaque at the location of the IMB experiment honoring the birth of neutrino astronomy. So there I am next to the plaque. This was just happened this summer. Uh, and as you can see here, it talks about 170,000 years ago, the supernova, the IMB experiment saw the neutrinos, and the IMB experiment was like 2,000 feet below this sign, right? And also in Japan, they saw it. And this was the birth of neutrino astronomy. Okay, so we now have 1987 supernova neutrino astronomy, 1989 solar neutrino astronomy. So how do we move forward? Well, because of the successes of these first generation experiments, second generation experiments were built. So in Japan, they built an experiment something like 50 times as big, with twice the density of phototubes, and it's been in operation since 1996, and it's still running. And although I was out of physics for like 35 years, I'm now actually back and working with some people on that experiment, and actually involved in looking for neutrinos from the sun, trying to go to lower and lower energy. But the big, the big item related to this experiment was now they were able to really study the cosmic ray neutrinos interacting detector and looking at that muon deficit, and they were able to show, without a doubt, that neutrino oscillations were occurring, and also able to measure several of those six parameters that I talked about. The Another experiment built around the same time in Sudbury, Ontario. This was made of heavy water, and the great thing about this detector was that they could measure two things simultaneously. So they could measure an electron neutrino interacting, sort of like the way we did in 1989, but they could also measure what's called neutral currents, which would be identical to all neutrino types, because there's no chart. You're not creating an electron or a muon or a tau. So an electron neutrino or a muon neutrino or a tau neutrino can all interact with neutral currents. So if you can measure that neutral current interaction, the ratio of electron neutrino interactions, you could sort of definitively show that you really had electron neutrinos oscillating, independent of any solar model. And they were able to do that. And so these two experiments definitively showed neutrino oscillations, and they won the Nobel Prize in 2015. Uh, and the head of, both experiments won, and the head of the experiment in Japan was actually a grad student that I worked with back 30 or 40 years ago, on the first Kamioka experiment. So, okay, so now what are we going to do with a super Kamioka and other neutrino experiments that have been built since, towards neutrino astronomy? Well, one of the things we can do is an early supernova warning system, because when this supernova occurs, the neutrinos come out very quickly because nothing really stops neutrinos. But the photons of light, they take a little longer to get out of that star because there's just so much going on in that star, and they're interacting with everything. So the light doesn't doesn't get out from that center, place where this collapse is occurring. Doesn't The light doesn't come out as fast. Now, what does that mean? What does fast mean? Minutes, potential, maybe even hours, but certainly minutes. So multiple neutrino experiments have set up this early warning system where they have online, see a cluster of events, they can reconstruct it very quickly. They can sort of tell the direction to within a degree or two, and it sends out an email alert to all the astronomers to say, hey, a supernova is coming, and where, in what direction to look for it. So that's a great thing if in fact we do get a supernova. Uh, this can, see, it can certainly see as far as the Large Magellanic Clouds in any of these nearby galaxies, the Milky Way, but the closest large galaxy to the Milky Way, the Andromeda, sort of at the edge of this being possible. I'm not sure, it's probably not possible really to do it there, and certainly nothing further away. So we're talking about mostly, Milky Way and nearby galaxy neutrinos. But we can get even an earlier warning, because when we're in that last mode of burning silicon into iron, it happens over a period of days to weeks before, when you start doing that till you run out of the silicon. And therefore you're getting a lot of stuff's happening very fast, a lot of neutrinos are coming off. So this could be detectable in one of these detectors. And uh, now here we got to be pretty close. So we're not talking about 170,000 light years. We're probably talking more like 500 or maybe even 1,000 light years at most. But we could now get an early warning that's as much as days with this, and Super Kamikaze has just implemented this. Uh, well, anyway, so far There haven't been any supernovas since 1987. These alarms aren't going off. Uh, but there's sort of a sub-alarm, that doesn't get sent out. So everything's working, but we're just not getting a significant number of neutrinos that would be indicative of a supernova. And there haven't been any. So it's not like we missed them. Well, so supernova early warning. What else is going on? So I was talked about this at the beginning. We can't see any, like I said, supernova beyond, and maybe Andromeda is sort of like the limit of what might be possible. Uh, but we see new supernova all the time optically from in light years, galaxies billions of light years away. Uh, and there are billions or trillions of galaxies in the observable universe that have had 14 billion years to have supernovas. So there are supernova neutrinos just scattered throughout the cosmos. They're coming at us from all directions, from something that happened a very long time ago, potentially, and sort of to some extent like the cosmic microwave background, although that just happened at one point in time. But this happened. This has happened continuously over time since the first galaxies were born, the first stars were dying. So, can you detect these? Maybe. There are calculations that show numbers that are sort of possible to be detected, and several experiments have reported limits on, how many there would be, and these limits are getting very close to what those projections are. So it might be possible for the end of the decade that we do see neutrinos. We do see this diffuse the supernova neutrino background. Okay. Just to move on. So, we're talking mostly about lower energy neutrinos because at least this is low in the sense of a high energy physicist. But cosmic rays were very much higher energy. Uh, how do they get created? Well, that's not fully understood, but there are, obvious, there must be stellar or galactic processes that are creating all these high energy cosmic rays. They could also be creating neutrinos. But when you have these higher energy particles, we need a bigger detector because we want to measure the energy of the neutrino. So by measuring the energy of all the products of the interaction, and they're going to move through the detector because they're so high energy, well beyond the size of the detectors we're talking about. So we need something much bigger, like a kilometer in size. How are you going to do that? Well, they came up with this great idea called Ice Cube. And they built this detector at the South Pole. It's been running since 2010. Actually, Antonio was going and visited it. Uh, so this is uh, in the ice in the South Pole, and the actual detector part is like a mile down in the ice. And the detector part is something like a kilometer on a side, and it has the same idea of Cherenkov light. Particle neutrino would interact, would make particles. The particles are relativistic. They give off Cherenkov light, and uh, they'd be able to you'd be able to reconstruct the direction of the particle. You could contain the energy in your kilometer of detector. You can see neutrinos. Uh, well, you can reconstruct and find the direction neutrinos are coming to probably better than a degree. So and the thing that may not be obvious, but the ice is relatively transparent. Now you can't do the same thing you did in the other detectors. Have the light detectors only on the outside. You have to scatter them throughout this volume because they're not that transparent. But so they got 5,000 of light detectors that they put in here, and they're able to do this. So the here's a picture of one of those light detectors. And so what's happened since they've been running almost 15 years? Well, they announced in 2017 that they saw a real high energy neutrino that they believe came from a galaxy far, far away, because at the same time, a gamma ray experiment uh, saw a blazer flare coming from that location. Of course, within a degree, uh, but that, pretty indicative that this was associated, with that event at that galaxy billions of light years away. And when they continued looking in that direction, they reanalyzed all the data. There did seem to be an excess of high energy neutrinos coming from that direction. Not an enormous excess, but a sort of a statistically significant excess. In 2022, they announced an even bigger excess that appeared to point back to another galaxy, a closer galaxy, uh, over detecting over all the years of their detection. So, so we at this point, potentially now we've seen two high energy, very high energy neutrino events or sets of events that are coming from distant, stellar or galactic events that are, well beyond anything that, we could otherwise see. Now, this idea of having a kilometer-sized detector, so they did it in the ice. They also built a detector in the Mediterranean, and there was a first generation. Now they're in the process of turning up a second generation detector in the Mediterranean. They're talking about building a detector in the Pacific Ocean someplace. So, so this idea is going to keep going and have a, more data as time goes on. Okay. What about other gravitational waves? All right, so we now have gravitational astronomy. We've been able to see gravitational waves from uh, neutron star black hole mergers and so on. Well, those events maybe could generate neutrinos also. So can we find any neutrinos in coincidence with events from the LIGO, other detectors? Low energy or higher energy, at least so the Kamioka experiment looked for it, and well, so far hasn't found anything. But there's certainly a potential here that we will see something in the future. So that's all I have for today. Uh, I'm sorry, I don't know if I talked fast enough, but I know we started very late, and I haven't given anyone much of an opportunity to ask questions. But certainly now is time to ask questions. So,
Could you put back 2 slides to that last picture of that detector?
Oh, yep,
well,
you heard that
That's
one,
it?
that one.
That's it? Thank you very much.
or the one before it, I can't hear.
Thank you.
Yeah, he just wants to take a picture.
Oh, okay.
The detector.
Got it. Thanks.
Awesome. Yeah, so it's open for questions. However you wanna land, Bruce? Yes, go ahead.
Significance of the diffuse neutrino background.
So,
Okay.
so you're going to have to repeat it, Antonio.
Yeah, so I'll repeat the question. So what is the significance of the diffuse neutrino background that you talked about?
Well, well, there is, multiple things that are happening. One is whether, rates of supernova have been, sort of constant over the course of the universe. The course of since the Big Bang. There's, well, or at least the models maybe don't have obviously the beginning, close to the Big Bang, you didn't have galaxies and stars. So, but all that's built into the models that were there. So can sort of understand whether those models were correct. The models have, do things like uh, change the energy of the neutrinos as the as as the universe is expanding, right? So, as just as the light is being redshifted. The neutrinos are being redshifted, so that see whether that would happen the same way. The and and then the number again that now you'd have a complete uh, uh, oscillation would occur. So there's a lot of things that go into this. Of course, you only get one number really. I mean, there's an energy spectrum as well that you can measure, uh, but it's gonna. Where wrong? I'm not on that wrong page. So it's one of many things we can do to learn more about neutrinos, but also learn about the supernova and other things.
Okay, does that answer the question? Okay. Additional questions?
I have a question if you can hear me.
Yes.
Hi,
yeah.
Lucas.
Hi, Bruce. Hi, Antonio. Thank you again for, this amazing presentation. This is, wonderful stuff. Bruce, you may have touched on this, but, just as we have the CMB map, the cosmic microwave background map, that essentially, allows the verification or other, leads us back to the Big Bang. Along the same lines, can we say that, detecting neutrinos will allow us to understand the Big Bang better? Is that something that you've touched upon, or maybe?
Well, yeah. So in fact, I haven't touched upon that. So the neutrinos here in occurred well after from the diffuse supernova neutrino background occurred well after the Big Bang because you had to create galaxies and stars, and they had to go through a lifetime, and so the earliest neutrinos are well after the Big Bang from this. But there certainly or potentially neutrinos created at the Big Bang there. And then you one of the questions people would obviously ask is, oh, well, neutrinos have mass and they're pretty dark. And we have this thing called dark matter, right? That no one really understands. Can that be neutrinos? So at least at this point in time, with our best understanding about how many neutrinos are around from the Big Bang and what the mass of the neutrinos are, they're not enough to explain dark matter. But there's also the potential that there are other neutrinos that we don't see, right? So there's these three neutrinos, but people have talked about the potential of having things they call sterile neutrinos that don't really interact with the other neutrinos. So it's, of course, if they don't interact, how am I going to be able to see them? But there may be indirect ways of seeing them. So there are potentially neutrinos could, be part of answering, many of these open questions in cosmology, which in fact seem to have gotten more open recently with what's called the Hubble. God, what's the word? I can't think of the word. Where the measurement
Hubble
of the
tension.
the Hubble tension, right? The measurement of the Hubble constant from the cosmic microwave background versus the measurement from looking at supernova and going out distances and how they, the redshift curves change. Those two measurements have a very statistically significant difference, and with the new data from the Webb telescope, they it's the statistical significance has gotten worse, more in terms of there being a very real difference that somehow needs to be explained. And will neutrinos be part of that explanation? It's hard to say. We still have a lot to understand about oscillations. Like I said, there were 6 parameters. One of the parameters is associated with something called CP violation, which could have implications for the fact that one of the many unanswered questions is why we have matter in the universe and not antimatter. Why didn't everything just destroy? We have equal amounts of matter and antimatter, and they would have just destroyed each other, and we sort of have nothing in the universe. So why is that there? Well, it could be related to CP violation and neutrinos, but we don't know, but we haven't been able to measure anything, whether neutrinos have that, and then of course the mechanism how that could actually lead to the matter antimatter asymmetry. I mean, there are so many, there are neutrinos, have potential of being involved in, many different astrophysical implications, but who knows how it will turn out, and it may not turn out, maybe another 100 years before we really understand all this.
Yeah, thanks, Bruce. Thank you.
Yeah, I heard that the measurement of the Hubble constant by two different methods, it used to be the error bars would overlap, but now they're getting so much better that there's no overlap. And I guess this Hubble tension, because which one is right or what's going on? So it's fascinating, the neutrinos. I read something, but I'm way out of my element, that apparently neutrinos interactions might actually be affecting the structure of the cosmos itself. But I don't even know how, if that's even a proper question to ask. So
But yeah, well, I'm not. Yeah, I mean, there's certainly a lot of people with, trying to throw neutrinos into theories, and maybe one of them is going to be correct. We've been looking for dark matter. There's been a lot of theories on dark matter, and and yet no one, and a lot of experiments trying to look for it, and yet at this point, so far there's been nothing. It's a lot harder to find dark matter than neutrinos, and neutrinos are pretty hard to find. Uh, so maybe it's just a question of time, and maybe the idea of dark matter is just wrong. And because people come up with ideas that say, well, maybe gravity should, if you modify gravity, uh, that may explain, the dark matter. But it's sort of very hard to modify gravity in a way that's consistent with all the experiments. Everything that we measure about the cosmos.
other people online, feel free if you have questions. I'm looking at the audience as well. Additional questions? Yes, go ahead.
Yes, I was gonna say about the neutrino, what did you use to measure the neutrino? Because it's supposed to be, unmeasurable with the, current devices.
So I'll repeat the question. So a gentleman is asking, what was used to measure neutrinos? And you have a slide there.
After it comes diffused, that, I think, yeah, after it comes diffused.
There.
What did they use to, do the measurement?
So go ahead.
Well, so I mean, the first, we can go back to 1955, right? That was the first experiment that was able to detect neutrinos. So, so neutrinos very hard to detect because the cross section of interacting is so tiny that you need to have zillions of neutrinos going through your detector before you're going to have any of them interact. But the thing called the weak interaction says how they interact. When they do interact at a very small cross section. So, you have a neutrino, let's say a neutrino we'll go back to 1955, from a fission reactor. Actually, that happens to be an anti-neutrino, but let's not worry about the details. That neutrino comes in, a zillion neutrinos come through, but one of them decides inside your detector, it's going to hit electron or a nucleus, and it's going to make an electron and maybe some, break up a nucleus in some cases. And this detector will see, it doesn't see the neutrino, you don't see the neutrino, but you see the products of the interaction. You see the electron, and maybe a neutron might be knocked out of a nucleus or proton knocked out, and you might see something like that in some of these detectors. So, it's been, that's effectively what's happened in every detector. They have different mechanisms, but but the first step is the neutrino interacts, creates a set of particles, and then that are well known, well understood particles, and those particles give off energy in a detector, and that energy in the form of light or something else is able to be detected by the elements of that detector, and be able to tell that you've seen particles that have appeared in the middle of, they appear in the middle of the detector. So you assume, especially since you presumably are working at a place that has a lot of neutrinos, you assume that, boom, it was a neutrino that caused that particle to suddenly appear, out of nowhere in the middle of your detector. I don't know. Does that answer the question?
Yes, so you're detecting it at the speed of sound or the speed of sight? I mean, the speed of light.
Well,
Charcoal
the
radiation.
particles at the energies we're talking about, and the particles that are created when the neutron hits an electron and nucleus, and boom, they whatever particles are made and they come out, they tend to be pretty energetic. Well, it depends, but let's stay with the electron. The energies of the electron make the electron very energetic. So, so it's going close to the speed of light at the beginning, in any of these kind of experiments. But it's different detectors detect things differently. I mean, there are experiments that are trying to measure very low energy neutrinos that have other kind of detection mechanisms. I'm not as familiar with the details of those kind of experiments, but these kind of experiments, the neutrinos the particles that are created from the neutrinos, are moving pretty quickly and giving off a lot of energy in the detector, and some fraction of the energy they give off then is detectable by the detector and able to tell you that you've seen a particle. And so so in these kind of detectors, the things that you're seeing happen pretty much at the speed of light, right? So so within nanoseconds, right, of the particle being created in this detector of this size, the light that are generated by those particles are detected by these little detectors here, and then within again maybe hundreds of nanoseconds, an electrical pulse comes out of these things, that then we have a wire that you can't really see here that comes up all the way to a bunch of electronics at the top of the detector, which then is able to record the fact that this thing saw the light, and we're recording it for all 2048 simultaneously. And within hundreds of nanoseconds of the thing occurring, all that is detected and recorded. And at least that's how these kind of detectors work. Not all detectors work the
So they're
same way.
really sensitive. Oh, that's pretty interesting.
Okay.
Oh, thanks
And
for letting me know about it.
and how do you, I mean, since you have so many events, you have to rule out some of them, right? That this is not.
Well, most of the events that we see underground, even 2,000 feet underground, are actually remnants of muons. So the cosmic rays that are creating muon neutrinos are also creating muons, and muons are one of the longest lived of these short-lived particles. They have a lifetime of microseconds, which sounds like a really short time, but because they're relativistic, the lifetime is long enough that they're able to get down into the detector. At least some of them are, and this detector would get around one muon entering the detector per second. but they're all coming, hitting the top. They're coming down from the top. So you're pretty much able to tell the difference between something that enters at the top versus something that happens in the middle, right? So the vast majority of those events, uh, the 1 a second events, you can get rid of, unless you really get confused on one of them and say, oh, that didn't happen at the edge. It happened, a meter in from the edge or 2 meters in from the edge. But at some point, you don't make mistakes that big. So so actually, you sort of draw a box 2 meters inside of these phototubes, and you call that the fiducial volume, and you only consider events that are happening in there as the ones you're interested in. So that really just are the neutrino interactions and the potential proton decays. Well, and I should not forget radioactivity. Uh, you go to a mine, you have radon in mines. The radon gets dissolved in water. The radon decays into a whole bunch of things and gives off uh, radioactive things, but they're really low energy, so you can sort of suppress them unless you're trying to do what I'm doing now in my current experiment, uh, trying to lower the energy of looking for neutrinos from the sun. So we're banging up right against those the radon-induced radioactive backgrounds. But for everything we've talked about here, we're well above that, and really the only problem, are trying to find well, trying to understand the one neutrino interaction a day. And, while it was originally a background to proton decay, it's now become the most interesting part of the experiment, trying to, use that one neutrino a day to, understand neutrino oscillations. And what I forgot to mention, uh, in the Japan experiment, one of the things they've done is that they have an accelerator in Japan that they can create a beam of neutrinos and aim those neutrinos at the experiment. So that's actually running simultaneously. Uh, and so you're able to see neutrino interactions from, coming from that accelerator a few hundred miles away. And well, another way of measuring neutrino oscillations.
Do we have another question from the audience? Yes?
There's a nice little website called All Things Neutrino. It has
Hmm.
a very excellent little description of the different ways they're detected.
Okay.
Flashes of light, different interactions, there's many different ways that it happens. But the site is called All Things Neutrino.
All right. Well,
All
thank you.
right, thank you.
Yeah, thanks for that. Yeah, so I guess you focus on light, but you also, I think you mentioned that there's chlorine atoms are changed, the cleaning fluid.
Yeah, I mean that was one experiment.
Yeah.
There was another experiment with gallium.
Geez. Wow.
Let's see, and another experiment with boron.
Oh my God.
So there were a lot of experiment, and those experiments were able to, at least looking for solar neutrinos, were able to go lower in energy. Because they would sort of change atomic states, in those materials when those neutrinos interacted, and would be different, among the many ways of detecting. A new detection, experiment that's under construction now. The
Mhm.
biggest experiment in the US that's under construction now is called Dune in South Dakota.
Oh,
Is with liquid argon. That's what they're using.
okay. We have another question from the audience. Yes?
Let's say the warning system goes off and because we're detecting a supernova nearby, what would your day be like, Bruce? If that warning system
What would my day be like? Was that the question?
Like if we got that warning, maybe silicon turning dying close by.
Well, let's say Betelgeuse, goes
Let's
supernova.
hope it's not too close, but yes.
Yeah, right. So if something is within, I don't know, 50 light years, something like that of the Earth, a supernova would probably kill all life on the Earth.
Yeah.
There's some, I'm not sure the exact number, but
Goodness. Betelgeuse, I think, is about 600 some light years away.
yeah, so we're safe. We're safe from that, and probably, I don't, I haven't really done the calculations. I'm not 100% sure that we could even record all the neutrino interactions that would occur, because you would get, I don't know, like a million neutrino interactions in 10 seconds.
Oh,
And
yeah, something outrageous. So I'm gonna stop it here. For those that want to continue asking questions, certainly you're welcome to. So I want to say thank you so much, Bruce, for your talk. It's very impressive and it's actually super exciting. Some new aspects of astronomy that I had no idea, but it's wonderful to see these developments. So even though the experiment did not succeed originally as intended, you've discovered some new amazing things. So thank you. Thank you very much.
thank you for inviting me.
Okay, so let me, I'll stop.